ja sam, gledajte, pošto piše da sam applied scientist, akcenat je na applied. Znači, više sam applied, manje sam scientist. Stvari koje ću pokazati, koje izgledaju dosta komplikovano, su više tu za ilustrativne svrhe, tako da ne moramo da idemo u njih, to jest ja neću ići duboko u bilo kakvu teoriju. Sad ću da prebacim se na engleski. So a little bit about me. Something was already in the email which introduced the talk. I studied College of Engineering in Belgrade, graduated. My major was electronics, but there also I started working with images because my diploma thesis was a compression of fingerprints. And then I came to Boston in 2000 and got a PhD from Boston University. Actually, I worked closely with Nikola. So I'm glad that he's here, but I also hope he will not ask me anything. And the dissertation was related to tracking of objects in videos. After graduating, I joined a startup in Cambridge. The startup was acquired by a bigger company, which was a conglomerate. We continued working on video analytics problems applied to retail. Then I switched to a medium-sized company. Well, actually, it was a late-stage startup because they became public while I was there, which was in healthcare space. That was in Privata. And I worked there on some face detection-related problems. And then there was a big shift for me when I joined Amazon in January 2016, because I joined a confidential project. I had no clue what I'm joining. It turned out to be Amazon Go, which was at that time confidential, became public a couple of years later. So this shop, which doesn't require you to actually pay anything, except you do pay, but automatically everything you do in the shop is tracked, and the items you're taking and added to your virtual cart. I'll show some examples later. And then in 2020, just before COVID, I moved to Alexa, just because office was closer to where I live, but turns out I didn't have to go to office for 3 years. Well, hindsight is always 2020. So, so a little bit of AI, and why do I have this slide? I mean, I'm trying to do this presentation because I see a lot of, this slide is there to dispel this kind of like, what's AI? And people are using that for so many different things, but there is a very, there are a lot of definitions, obviously, but one definition is science of engineering or making intelligent machines. And I don't think we reached, by any stretch of imagination, that point that we have intelligent machines. So when you hear commercials about AI for this or for that, and when you're sometimes even we are selling products as being AI, that's a little bit of a misnomer. But machine learning is not misnamed. It's the part of AI studying, which is basically how computer agents can improve their knowledge thinking actions based on experience and data. So machine learning is learning from examples. So we're teaching machines by providing them examples. And we either provide them examples and desired outcome, supervised learning, or we just provide them the examples and hope that they figure out what's going on. And that's unsupervised learning. And there is also, I just have to move this video up, sorry, because it's in my way. I don't know how, okay, I can minimize it. But there's also reinforcement learning, which lets machine learn through rewards. So if it's successful in a task, it gets a positive reward. If it's not successful, it gets a negative reward. And that's involved with teaching computers to play games. Now, going a step further, a part of machine learning that has been very successful recently, more recently, in the last 10 years or so, is deep learning, where artificial, obviously, neural networks are used and trained to solve a lot of different machine learning tasks and AI tasks. So there are other definitions which are interesting is the narrow AI versus the artificial generalized intelligence. I mean, the AGI actually is pretty new to me, that as a term, but I think it makes sense. Narrow AI is a systems which solve one particular problem. And for example, facial recognition, speech recognition, or some other task which is very narrowly defined. But human level AI, AGI, would be designing a system that can mimic a human and basically can solve many tasks and also become not conscious, not that type of AI, but very context aware. I mean, basically, I think chatbots is one example, but I would say that maybe even if we would get to fully autonomous car, although that seems like a narrow AI, it will be a path toward AGI. Sorry. Okay. So I will go over this very quickly. Between end of my undergraduate and 2020, I was working computer vision. That's why I will emphasize a little bit that part of machine learning and artificial intelligence. And I'm not going to go through all these dates. I actually found out about some of them while researching this talk. But it's interesting that a lot of initial understandings came from different fields. In its neuroscience, it's basically people were researching how do humans see, and that helped inform the algorithms. So in 59 already, we understood that simple structures such as oriented edges are important, and that still holds true. I mean, yes, neural networks are huge, and we don't exactly know what each layer does, but initial layers really in convolutional neural networks detect edges. And so I found it funny how in 1966, a professor at MIT, Packard, decided that, computer vision can be solved over a summer. Students are smart, they're going to do it. They didn't do it in 3 months somehow. I don't know how they didn't accomplish that even at MIT. But it was almost the birth of the computer vision as a scientific field. And so in 80 here, I'm sure there are other dates, and I'll show those dates related to development of neural networks. But first convolutional neural networks were introduced. And about the same time in 82, this concept of hierarchical algorithms and that basically the vision works in a hierarchical way was introduced, and is still holds true, and it's used in modern designs. So now, in more modern times, Jan LeCun in 89 applied a backpropagation algorithm to a convolutional network, and in 95 he published LeNet5, and it's a first modern CNN. And at the same time, MNIST dataset of handwritten digits was created. Now, what's interesting here, it's 89, 95, but really, when I was studying in the early 2000s, nobody was talking about neural networks. So, though they were invented much a long time ago, actually, only in 2012 they became really popular. And what happened in between? I mean, some other important results, like in 2001, Viola Jones face detection algorithm, which worked very well in real time and allowed a lot of face detection applications. And after that, in 2006, people started realizing that they need to publish data sets. The field of computer vision needs to become more organized, and you need competitions with the data sets that the competing groups and algorithms can compare each other. And this was a data set on object classification. And similarly, Faith Ely, she reached the same conclusion that really field needs a large data set. It's not just about algorithms, it's a lot about data. And so she collected and published the ImageNet dataset with 12 million images with 22,000 categories and launched a new competition. And so that competition launched in 2010. And then in 2012, a team from the University of Toronto, under supervision of Professor Hinton, and he is one of the pioneers in neural networks, has a lot of results before that, but this is the most important only in a sense that the AlexNet they presented beat the next best algorithm by almost 10%. So the competition was to classify images into 1,000 categories. What are the categories? Cats, dogs, houses, and things like that. So this original 22 categories, 1,000 categories was cut to 1,000. But it was a huge result. Like no other algorithm was ever better than 26% accuracy. And this was 16%. And a few years later, it was like 3%. And really, at that point, first convolutional neural network was shown to work very well. By a few years after that, if you went to CVPR, Computer Vision Pattern Recognition Conference, you will see that over half of the papers were using neural networks. And then probably a year or two after that, you'll be hard-pressed to find any papers doing anything else. And so that was a complete change in the field starting in 2012. And a couple important, there are many important results afterwards. In 2014, Goodfellow introduced generative adversarial neural networks, which can be used to generate images with the style of another image. It's important because it has this concept of one network is trying to generate a fake image, which is going to fool the other image, which is going to discriminate between fake and real. And then very recently in 2022, a group from Munich developed stable diffusion algorithm. And this is a text-to-image model. It generates images from text based on diffusion techniques. And so this is, I was trying to show the difference between 1959 and 2022. So on the left is one of the first ever digital images. And that's Russell Kirsch's son. And on the right is this beautiful image, which is completely fake. And it's generated using stable diffusion with a text prompt saying, photograph of an astronaut riding a horse. And you get this image. So you can see how far computer vision has advanced. Now, this is generative computer vision when you're generating images. Of course, the other side of it, analyzing. There have been a lot of advances there, recognition, classification, tracking, and so on. And autonomous vehicles are using all of them. Now, that said, as even on any other field, there's a lot of hype. In the same conferences, we were told that, by today, most of the jobs will be replaced by AI and most of the cars will be autonomous, and none of that happened, obviously. So taking a step back, this is going to be a little bit about me. And I call this good old times for a couple of reasons, because it was good being a PhD student 20 years ago, but really because this was a very complicated formulation. And at the time, a lot of formulations in computer vision were very mathematical. So you have this data term, then there is like a regularization term. My research was trying to segment video into moving objects which undergo occlusions, like this car, which is, as it's being driven, being occluded by a building. And I was doing that using active contours and level sets and sort of the original formulation active contours is like partial differential equations and forces which morph those contours. Then it's a little bit easier with level set and then it gets discretized. So it's very complicated. And this is not how computer vision looks right now. A lot of people who are practitioners of computer vision download a model, neural network model from the internet and just run a couple of lines of Python code. Not to say that's the research, but that's how things are often done. Sorry. And this is my first real job. So it's also good times because it was a startup. And it was video analytics in retail environments, meaning there's a lot of surveillance cameras in the stores. There isn't a lot of people who are looking at what's going on. So you have this screen on the left with 16 camera views. It's all like 320 by 240 pixel resolution, very small. It was all on-premise. There was no cloud at the time. So you had these racks with servers. And we were trying to help by tracking people. And then once you are able to track people around and see if items are taken or left behind, you can also detect if people are stealing, or maybe if this would be applied to some general security, you can detect if somebody left a bag and that bag might have a bomb or something like that. So this is how our tracking pipeline looked like. And these are examples of some simple algorithms where you have a video, it's a static camera, therefore you can build a model of the background without any moving objects in the scene. And then people enter the scene and you can detect them, and then you can put a bounding box around them and you store them in some SQL database, and you have their position over time. And then later from that information, you can do some queries and try to figure out what has been going on in the scene. This actually is the kitchen of that startup. We really didn't have fancy offices at all. So this would be an example of application. You have a video, you want to see when a car enters that area or passes through that yellow area in the image of the left. Maybe you want to count the number of cars that have entered the parking lot. And so because you're tracking those cars using the algorithm I described before, you're able to get both an alarm if a car shows up which is going in certain direction, or just count how many have passed. So then I moved to this other company I mentioned, Privata. So they were basically a single sign-on company selling to healthcare. So healthcare has specific rules about privacy information, and you really want to keep doctors' computers locked. I mean, they should not leave their workstations unlocked, or they should not, whenever they're not in the room. At the same time, if they're spending a lot of time logging to all the different applications, and I can tell you that healthcare software is not that great, that was, waste the time they can spend with patients. So Imprivata developed a way to sign into a lot of different prescription, not just prescription, but also medical records, websites and applications like Epic. But they also wanted something more technologically advanced. And we developed this system where user space would be used to unlock and also lock the workstation. And so at that time, face detection was not considered to be accurate enough. So it can be used as a primary authentication method. So fingerprint or prox card, basically the card you use to open the building, was used as a primary method. But once you have logged in using your fingerprint, let's say, then if you leave the terminal for 10 minutes and come back, you don't need to scan your fingerprint again. You can just unlock it with your face. Because at that point, it's not really identification, it's sort of a verification and a re-verification. So this was our system we developed. When I say we, it was basically, I continue to work with my colleague, and there was one QA engineer. There was a small team. And what's interesting with this camera, it was time-of-flight camera. It was very popular at that time. Similar technology was used in Kinect, which was with Xbox, where games were developed that you can control characters with your motion. So here, a couple of things interesting. This camera is a depth, is a 3D camera, gives you depth, gives you distance of the object from the camera. It's also near infrared, so it works very well in dark. That allowed us to both latch on to the nearest face and also to be able to recognize. So basically, if you have multiple people near terminal, you want to actually check the face of the person who is closest. You also want to see if somebody is moving away from the terminal and lock the terminal. So that was important. But you also want this system to work under any light conditions, and near infrared is better for that than actually visible RGB image. So again, going back to history. This is not the history of computer vision. This is the history of neural networks. And I mentioned some of the points, like here it says 98 LeCun, but I think it was 95 in my previous slide. And 2012, AlexNet, 2014, GANs, UNet after that comes, ResNet in 2015, I'll talk a little bit about, BERT 2018, 2020 is GPT-3, and GPT-3 is the language model, but ChatGPT is probably what you have heard about in 22, and I'm guessing everybody has heard about or used ChatGPT, so I will talk about it a little bit as well. So how do convolutional neural networks work? This is the architecture of the AlexNet. So input is an image. Image has three channels: RGB, red, green, and blue. And so convolutional neural network, as the name suggests, is made from convolutional layers. So convolutional layers is just, imagine a filter which is being moved across the image. And it's not just one filter, but it's a filter bank. So when you see this 55 by 55 by 96, that's because a filter size 11 by 11 is applied in the first step, and it downsamples image from 224 to 55 because you're skipping, you're not applying this convolution at every point, but you apply it with some stride, with some step in between. But the main thing is there are several convolutional layers. First one looks a lot like edge filters, for example. But then later on, it's much harder to understand what these filters are actually doing. It's hard to analyze what features in the original image they're looking at, because as you go from left to right, the support becomes smaller and smaller. And then after this, in this case, 5 steps of convolution, you have these dense layers. Now, what are the dense layers? That's each layer is a linear combination of all the points, points. Okay, let me take it back. It's fully connected graph between previous layer and next layer. So you are combining all the points in the graph on the left side with the points on the graph on the right side. I wish I provided a demonstration of a fully connected layer, But think of it as that it's linearly combining all the values at that point to produce the values in the next step. What do you get at the end? Why do we do all of this? We get this representation, which in this case, it's a vector with 1,000 elements. And the idea is that somehow you have encoded all the useful information which existed in the original image. And that image had, let's say, 200 by 200, that's 40,000 times free channel, that's 120,000 points. 120,000 points are now encoded with a vector of 1,000 elements. But it contains all the information. You transferred this 120,000 into a different space with 1,000 dimensions, which contains all the information of the original image. And it's packed in a way that it allows us to classify what this image contains. So after this, at the end of this, that's why I made a mistake here. I'm sorry. 1,000 is because there are 1,000 categories. Actually, the encoding is 4,096. So you pack 120,000 into 4,096, and then you're figuring out which of 1,000 categories from the original ImageNet challenge, because there are 1,000 different categories of objects you are classifying in the images: cat, dog, house, car, and so on, which one it is. So this 1,000 vector at the end will be a probability vector, and whichever class has the highest probability will be the one that you output as the result. So these filters are not predefined. You start with a network which has random. Usually people don't start with that, but you can start with this network, and all the coefficients of these filters and of these dense layers, which are combining previous vectors, they're all randomly initialized. And then you train the network. You train it by providing an image and then comparing the actual output with what you know to be the category of that object. And that's this supervised learning. I take millions of images. For each one, I know what's the object inside the image. I pass the values. I do these convolutions through the network. I see the output. Output is going to be this probability vector. I take the max probability, and I take the difference between that and what I expect. This is the actual category. And I take this error and I back propagate it through the network, and I adjust all the parameters. So, sorry, before I go on to the next point, I think here it says there are 62 million parameters. So there are 62 million parameters in this network. And you need a lot of examples to train the network, because all of them have to start with some random point and have to get to the actual good value, which will allow you to then, when you show images the network hasn't seen before, that it can properly classify. So you train on some data set, and then you can use that network for any image when you're doing classification task. So this worked very well. You remember, from 26% recognition error to 16%, and then 2 years later to 2-3% recognition error. But what people discovered was that networks which are deeper, have more convolutional layers, are better. But networks which are deeper are also harder to train. This error we compute at the end of the network has to be back propagated through all the layers. And the more layers there is more chance of something called vanishing gradient. So that basically you will not be able to properly train initial layers. You might train those layers all the way to the right, but those initial layers will get, your information will be lost while it propagates many layers. So then there was this modification proposed, and those are the ResNets, where in addition to the layers, you have to signal passing to the layers, you can also take a shortcut and skip them. It's kind of skip connections. And these modifications allowed people to train very deep networks. Now, each layer became smaller in the number of parameters. Instead of having 11 by 11 convolutions, you can have 3 by 3 convolutions. So networks became deeper, but having less parameters, and also being more accurate. Less parameters is very useful, because the less parameters you have, faster you can train the network, and less examples you have to show to the network. Why is the number of examples problematic? Well, each example is the input image and the output label, let's call it. Is it a dog? Is it a car? Okay, that labeling problem is pretty easy, but if you have to do it for millions of images, it takes a long time. That's why at that time, to construct ImageNet, Amazon Turk was used, I think, crowdsourcing method, where you would pay a little bit money or people would do it for free, and basically people would just label images. But if you have a very specific problem and you need to solve it, and maybe it's proprietary and you cannot crowdsource labeling, and you don't have a lot of manual labor available to do labeling, it's a big issue. So having a network which is accurate and doesn't have that many parameters is great. I'll just briefly mention autoencoders. Why? Because this is, while AlexNet and ResNet are supervised learning neural networks, convolutional autoencoders are unsupervised. The idea is you feed input and you expect that the output is equal to the input. So what's great about this? There is no labeling. You don't need to construct labels for your images. You just find images and train this network. Now, what's the goal of this? A couple of goals. The main thing is that the autoencoders have two parts. One is called encoder, the other is decoder. In the middle, you get, again, a compressed, smaller representation of the input image. And that representation, so similar to how at the end of convolutional network, it was just encoder, convolutional network is just encoder, you get a representation. And so one application is you can compress images. The other application is you can actually denoise images, because this decoder can be trained in a way that it produces clear images. And so that's a bit of a modification of the original autoencoder, but it's done very well using this technique. But what's interesting to note here is this concept of encoders, decoders. As I mentioned, we go here, this is really everything outside of that last dense layer is an encoder. Once you get this representation, 4096 vector space, then you have this called softmax, which projects that into 1000 classes. It's called classification head, but this is an encoder. Here you have encoder and decoder. And so now something a little bit more fun. What did I do in 2016 in Amazon? I was part of a team which was helping launch Amazon Go. So I'm gonna play this video for those of you who haven't tried or haven't seen Amazon Go. This video is actually from quite a few years back, maybe 18 when it was first released. But it's still on the internet, so.
4 years ago, we started to wonder, what would shopping look like if you could walk into a store, grab what you want, and just go? What if we could weave the most advanced machine learning, computer vision, and AI into the very fabric of a store so you never have to wait in line? No lines, no checkouts, no registers. Welcome to Amazon Go. Use the Amazon Go app to enter. Then put away your phone and start shopping. It's really that simple. Take whatever you like. Anything you pick up is automatically added to your virtual cart. If you change your mind about that cupcake, just put it.
Okay, so I see that I'm over time. I'll be very quick now. This is very cool. It looks great in this video. It was very hard to make. This is a very hard computer vision, and not just computer vision, signal processing problem. Part of the work, my team worked on decoding these barcodes, which were on objects. And that was hard because they could be occluded, they could be in flight, people will be moving them fast. Now I'm gonna just rush to slides because I have seen that I have spent too much time on this. This was great, but this was not, we were just a peripheral team in Boston working on this. But at the same time, we were developing this idea to solve this problem differently. So instead of constructing this big store with many cameras, many weight sensors, and everything else, why don't we solve this problem by putting everything on a cart? So when you shop, the store remains the same way it was before. There are no additional cameras, no additional tech in the store. All the tech is in the cart. So we built this prototype. We started with this prototype over here. We made this cart. It had a lot of cameras. This was extremely complicated, but great cart because it had really almost 100% accuracy because it was working with specially designed codes in infrared. And then we realized, well, the special design codes, you have to apply them to products. It takes too much money. That's not going to work. So we shifted to using regular barcodes on regular products. And this is me, sometimes in 2019, with all the car prototypes. This is how a lab looked like. And finally, in 2020, just about the time I left the project, this card was released. So this video is much shorter, but cart has 4 cameras. Whenever you put a product in the cart, it automatically scans it and adds it to your receipt, and you can just take the items and leave. Now, that avoids waiting in the checkout line, that avoids waiting at a self-checkout, and it's pretty cool. So I think I'm gonna skip over this. I'm just gonna mention transformers because, as you can see, these papers, this paper was published in 2017, and it has over 96,000 citations. So it's really important in our field. It revolutionized how natural language processing is done, natural language models. So natural language processing deals with understanding text. First, there is also part which you are recognizing speech into text, and then you're trying to understand text. And that's what Alexa does. And this paper and work really it allowed us to build better and more powerful networks which can do better understanding, and we are still working on that. BERT is another language model which came after transformers using that technology. Again, over 82,000 citations, although the paper was in late 2018, published on Archive. And so I will wrap up with this. This is a very, on surface, simple problem I'm trying to solve, which is if you have a written text, I want to convert it to a spoken text. And it is something that can be done using rules. You can think of regexes. There are some finite state transducers, FSTs, which are rule-based systems which do this, but there is a limit to accuracy. It's hard to scale it to different languages, so it's a problem. And more recently, we started looking into neural methods. Neural methods are fine, But the problem is if you want to make an application which does not allow for errors, neural models are statistical and errors do happen. So it's hard to transition to them in some cases when you actually need accuracy to be close to 100%. And just to show you something which is related to ChatGPT. So here we are developing different models, rule-based, end-to-end neural, hybrid, combining neural and FSTs, training, crafting, doing whatnot. And then you just tell ChatGPT what's the spoken form for 15 St. Mary Road. And actually it does almost perfect job with no training. So yeah, this is one example. It doesn't do correct transformation every time, but you can actually improve the model without training it using in-context learning, where you provide some rules as input. You in a natural language, in English language, you describe what you want to accomplish. So here I try to just say convert to spoken form. That has limitations, but works pretty well out of the box. If you provide examples like here and say convert using these rules and provide few examples, 2 examples are here, but you can provide, like, say 20. After that, you really get a very, very high accuracy, which is approaching or equal to human accuracy. And this is without having to train any network. You just take the network off the shelf, provide prompt, describe your task, and it does the work. And that's the power of large language models. Of course, there are downsides. What are the downsides? Look at the parameter model sizes. We talked about AlexNet having 60 million, and then ResNet's having 1.7 million. LLMs have billions and trillions. So ChatGPT has 175 billion, that's GPT 3.5, and 1 trillion, I think that's GPT 4. And none of these models is smaller than 1 billion. And I think to get actual good results, you need to use larger models, which are around 100 million, 100 billion parameters. So number one, very hard, very long process to train this model, very expensive. Not a lot of companies can do that. So in some sense, that's again, there is a little bit of monopoly going. There are some smaller companies like this Anthropic who are developing models, but both Amazon and Google have invested into Anthropic. So everything else is really either a large company or a startup which is supported with a huge amount of money. So that's maybe something for discussion at some other time. Thank you very much for your attention, and I'm sorry for running so much over time. I didn't realize that this is going to take more than 30 minutes.
Mirko, hvala puno. Ja sam shvatio da te nisam predstavio, mislim ja i Mirko, tu stvari moj brat smo prvi komšije u Šapcu i odrasli smo zajedno tako da se znamo ceo život, a Mirko je inače bio uvek najbolji đak i u osnovnoj školi i u gimnaziji i ima jako uspešnu karijeru. I pretpostavljao sam da će ući detalje i mislim da je bilo možda malo previše komplikovano za neke od nas, ali je bilo vrlo zanimljivo i hvala ti puno što si nam dao taj neki malo uvid u istorijat ovih modela. Da li neko ima neka pitanja? Mislim, ja se nadam da ima u stvari. Ne zaboravite da se unmute. Evo ja ću da započnem, ako nema niko drugi. Mirko, šta misliš o tome kada ćemo imati, ne znam, self-driving automobile na ulicama, s obzirom na sve ovo iskustvo?
Ja sam, nažalost, veoma razočaran oko toga. Kao što sam rekao, na CDPR, krajem 2018. 19. Mnogo kompanija su predstavile svoja rešenja, mnogo je researcha urađeno, mnogo toga, obećanja su napravljena, ali se još uvijek nije desilo. Mislim da je problem jako komplikovan. zato što mora da se istovremeno voze automobili kojima ljudi upravljaju, a koji su vrlo nepredvidljivi i kojima mašine upravljaju koje pokušavaju da reši taj problem. Tako da ne znam, pošto se nije desilo kad su svi obećali za 2-3 godine, sad mi se čini da se neće desiti još bar do 2030. Tako. Ali mislim da je, i samo da dodam, Amazon Go je takođe nije rešio problem kompletno, ali ono što sam naučio radeći tamo je da kad vidiš da ne možeš da rešiš problem koji je previše veliki, onda malo smanjiš problem. Tako da krenuli smo da napravimo supermarket koji sve prodaje, ogroman, a na kraju završili sa prodavnicom koja više liči na 7-Eleven, ali radi i nikada ne naplati previše para, više para nego što si uzeo proizvoda. Jako je bitno da sačuvaš customer trust i to je ono što je Amazon dobar, u čemu je Amazon dobar, a mislim da je isto to važi i još više važi za self-driving automobile, gde je jako bitno da ta tehnologija zaista dobro radi, jer ne bih želeo da se stavim svoj život u ruke neke tehnologije koja ne radi. To je moje mišljenje.
Nikola ovde. Hvala Mirko na toku. Meni je bilo super zanimljivo. Nekih stvari sam se podsjetio, neke stvari sam nove čuo. A kratko pitanje bi bilo dokle je Amazon Go stigao sa strane deploymenta, koliko radnji, je li to raste ili je to sad flat? Mislim, ja sam to koristio par puta bio, sve to je što si rekao, zvuči super. S druge strane, znaš, Amazon koji ima koliko desetina, stotina milijardi dolara godišnje revenue-a, da bi nešto zadržali, mora da radi nekoj skali. Naprimjer, ove lokalne radnje što su imali, koje su bile ne Go radnje, nego obične Amazon radnje, imali smo mi ovde kod nas u Burlingemu i to zatvorili posle godinu dana. Mislim, verovatno im nije uklapalo se u model. Znači, je li Go raste, ili je flat, ili u opasnosti da se ugasi? Šta je sa Go-om trenutna situacija?
Odlično pitanje, a znam da ti sad zaustaviš ovaj recording.
Da, evo pritiskam stop recording.